कुछ दिन के लिए जाएगी, बस वहां पे वही भाड़ा लगाने का जुगाड़ करना है। Hello guys, good evening. Can you hear me? Yeah, hello guys. Okay, Shreyas, yeah, I got your message. The videos you are not getting. Okay, fine. The problem is actually I'm not in Bangalore right now, so I have limited access to the internet. So that's why I'm not able to download it and upload it. So I'll ask someone, probably Akhil sir, to do it on my behalf. Okay, so you will get it soon. Okay, regarding the all the videos which is not been sent till then. Okay, Shreyas, and all of you. Yeah. Okay, so that's why I have my own constraint nowadays. A little bit difficult time I'm facing. There's some medical emergency. That's why I'm in, Delhi from the past 20-25 days. Okay, so that's why all these, difficulty I'm facing. But yes, you will get the video soon. Okay. So could you tell me what have we done last class? Where were we? Acha, we have to start with valence bond. Okay. So valence bond theory means that overlapping concept, right? Just a second, I'll put this in the chart and then just 1 second, please. So last class we discussed with VSEPR, and we have seen, that how the um, bond pair and lone pair in a given compound defines the geometry or shape of a molecule, and what are the factors which affects the bond angle, right? So we have seen 3-4 factors already, right? The next theory is the valence bond theory, because we are talking about the bonding theory. So valence bond theory mainly deals with the geometry and shape of the molecule. Here we are going to see how atoms forms a bond, right? This is the bonding theory, and the heading all of you write down. It is valence bond theory. Okay, what is valence bond theory? According to this theory, the molecules are formed by overlapping of atomic orbitals, right? So this theory is based upon overlapping of atomic orbitals, right? So atomic orbitals which contains unpaired electron, single electron, that overlaps and forms a bond. So atomic orbitals which contains unpaired electron. So orbitals which contains unpaired electron overlaps and forms a bond, right? Because the pairing is done when overlapping takes place, right? Okay, so when you talk about the overlapping of orbitals, atomic orbitals, so atomic orbitals, there are two types of overlap, okay? So next write down, overlapping is done, can be done overlapping can be done in two ways. The first one is axial overlapping, and the second one is lateral overlapping. Axial and lateral overlapping. Axial overlapping, we also call it as head-on overlapping. Head-on overlapping, and lateral, it also known as sideways. Okay, so first thing you write down here, we'll see what is axial overlapping. Write down, it takes place along the internuclear axis. Along the internuclear axis. Okay. Axial overlapping always forms sigma bond, right? The first overlapping between the two bond is always axial and it always forms sigma bond. So if you look at this geometry, this orbital overlap here, we have an s orbital and we have an p orbital. It is sp overlap, right? P orbital and p orbital. S and s orbital. This overlap. Okay, so this is along the internuclear. What is internuclear axis? If you join the two nucleus with a straight line, this line is the internuclear axis, passes through the two nucleus of the two orbital. Here you see, this line is the internuclear axis. This is also the internuclear axis. So the orbital or the overlaps that takes place along the internuclear axis, that is axial overlapping. Internuclear axis. This one is also internuclear axis. This one is also internuclear axis. And all these are axial overlap. This one is also axial. And this one is also axial. Okay. Done. Okay. Now in this one, the extent of overlapping, you see, if you see, it is the experimental order we have. The extent of overlapping, it is maximum for P, P, then we have SP, and then we have SS overlap. Once again. So this is the extent of overlapping we have. PP overlap. No, it's not, Pranab. FF overlap, first of all, we don't consider it, right? So overlapping depends upon the shape of the molecule. I'll tell you what it is. Shape of the molecule, not shape of the orbital, right? So it has been observed that when we have the lobe of dumbbell shape, that overlaps to a greater extent because of its shape. Okay, more area it covers when overlapping takes place, and more area means more extent, and hence the stronger the bond. Yes, got it. So extent of overlapping basically means that when the orbital overlap, the shaded area that I have drawn in the last slide, that area is more. That is the extent of overlap. Okay. What you have to keep in mind, that the first overlap that takes place between the two atoms in a molecule is always axial overlap. When axial overlap is done, then only we can have lateral overlapping. Without axial, lateral is not possible. It's not like the two molecules directly forms a lateral bond. That is not possible. Two atoms in a molecule. Okay. First, always axial, like you see, oxygen double bond if you draw, right? So how many sigma and how many pi we have here? One sigma and one pi, right? So sigma bond that forms here, that is because of axial overlapping. So this is sigma and this is pi. So this is axial overlapping and this is lateral overlapping, which forms the pi bond. Okay. So pi bond always forms once the sigma bond is formed already. That's why first overlap is always sigma, is always axial, that gives sigma bond, and then we can have lateral overlapping. Okay. So that's the one thing. Now, see, first of all, Vadhav, we are just looking at this theory, valence bond theory. There are drawbacks in this theory also. It did not explain the overlapping of d orbital. That is one of the drawbacks, and that's why we got the another theory here, right? Because of the drawback in this theory, we got the another theory, which we'll discuss after this. Yes, in valence bond theory, we did not talk about the DD overlap, right? We don't consider it here. Right, so obviously there are some drawbacks in these theory, like we had drawbacks in various atomic models. Okay, similar kind of thing you can understand here. So PP, SP, and SS overlap we have. Now the second type of overlap that I've already told you, it is lateral or sideways overlapping. Write down, it takes place once the axial overlapping is done. It takes place once the axial overlapping is done. Once the axial overlapping is done, and the orbital approaches each other, along the axis which is perpendicular to internuclear axis. Along the axis which is perpendicular to the internuclear axis. Okay, it always forms pi bond. Next time, it always forms pi bond. Okay, like you see, suppose we have an axial overlapping, PP overlap I'm considering. This is suppose the axial overlapping we have. Okay, so this atom has 3p orbital, right? Suppose this is PZ, right? This is the internuclear axis we have. And once the overlapping takes place, then the internuclear axis is fixed. This is axial, right? But this atom has two more p orbital present. I am drawing here only one just to make you understand. This is the another p orbital we have, right? So since the overlapping takes place along this line, that is along the internuclear axis. So now the internuclear axis is fixed. When these two orbital overlaps here, this overlap is the lateral overlapping, perpendicular to the internuclear axis. So this is lateral overlapping, and lateral overlapping, you see, it forms pi bond. Did you get it? No, see, lateral overlapping d orbital can form. We have d pi bonding. We'll see that later. We'll have d pi bonding, but usually we don't consider the extent of overlapping in d orbital. No, it's not possible for s orbital. Lateral overlapping is not possible for s orbital because s capsule has only one orbital. Right, so we always have a line which is passing through the two nucleus. So SS always gives you axial overlapping. Okay, if you try to understand this pi electron, suppose this is a sigma bond we have, right? This is a sigma bond between the two atoms, and this is a nucleus. The overlap that you have, the lobe overlap, it forms an electron cloud like this. This is the overlap, lateral overlap. Right? Electron cloud above this sigma bond and below this sigma bond. Electron cloud, right? So this is the electron cloud we have. Electron cloud, right? This collectively gives one pi bond. It's not like we have two pi bonds here. This two gives one pi bond. Are you getting me properly? Am I audible, guys? Is there any lag or something? Yeah, I think Madhav, it's your problem then. Yeah, okay. Maybe it will get fixed in some time. Yeah, fine. Let me know if it is if it won't go well in the class. Then I have to change the network actually. We'll see that once. If you have difficulty in understanding, just let me know, any one of you. Okay. Fine. So this is the electron cloud, this cloud that you have, right? So this gives you one pi bond, collectively gives one pi bond here. So pi bond is something like this. If you can, see me. See, if you have a sigma bond like this, you see, this is a sigma bond, if you can see, right? This is a sigma bond. So this is the axial overlapping. You see this, the lobes that overlaps like this, okay? It is axial overlapping. But the orbital which is perpendicular to this axis is this. When these two overlap like this, above and below also, when these two overlap, this forms a pi bond. Can you imagine this? Right. So we have a sigma bond like this, axial overlapping, and electron cloud here like this, because of lateral overlapping, and electron cloud here also below. This I have shown over here. Is it clear? Electron cloud is there because of overlapping. Okay. So this forms the pi bond always. Now, what is the characteristics of sigma and pi bond? Yes, it is mostly, but since Pranav, that's right. But since we do not we cannot find out the position of an electron. That's why we draw the complete overlap and we say the electron cloud is above and below also of the sigma bond. See, Vaibhav, electron cloud is the electron that is present in this region, right? Like this. Overlapping, the electron is present between the two nucleus in the bonding state because of overlapping, right? So overlapping is a property of an orbital which contains unpaired electron. But the electron cloud is the density of electron over here in this region. Right? Understood? Yes, Pranav, tell me. Yes, electron will be one side only at a time. But which side we do not know. That's why I represent it like this. Exact position we cannot find out, no? Right? The orbitals which has unpaired electron will take part in overlapping, and hence the electron gets paired. Tell me any doubt? Yes, Pranav. Yes, it is covalent. Yeah, shedding of electron it is covalent compound. Okay, next write down characteristics of sigma and pi bond. Copy down this. This table, you copy this down, all of you. Let me know once you are done. Done, all of you? Okay. Yes, pi bonds forms because of the lateral overlapping of p orbital, but not only p, we can have d orbitals also. But in valence bond theory, we don't talk about d orbitals. Point number 4. Acha. The molecular orbital is symmetrical about internuclear. Okay, so it is fine since we did not talk about molecular orbital. So this better you write atomic orbital here instead of molecular. But the statement is not wrong as far as molecular orbital is also concerned. But for this, for now, whatever we have done so far, molecular orbital we did not talk about, right? So better if you write the atomic orbital, right? But the statement is not wrong for molecular orbital. Yes, Aditya? Yeah, definitely I'll do molecular orbital theory, but we'll do one by one. Okay? We'll do it today itself. Do you have semester exam coming? Okay, when it is? Coming week. When is chemistry? Coming Tuesday. What is the portion? What is the portion for chemistry, guys? Okay, so all the 3 chapters we have done. Fine. So bonding we'll do it today. Okay, whatever is required for school exam, we'll do it today. Are you prepared well? Because Tuesday is like you have just 2-3 days, right? Okay, fine. Did you finish all of you? Acha, for HSR is properties of matter. Acha, states of matter they have done. Okay, fine, not an issue. Yeah. Fine, guys. So you see how this orbital overlaps takes place and forms the molecule. So we are going to see a few examples here. Oh, okay, fine. Okay, Madhav, I'll go back just a second. Okay, for HSR, the date is not declared, right? You said after 1st October, is it, Pranav? Okay. Okay, from the 6th, by then we can do that particular chapter also. Okay, not completely, but yes, we can do that mostly. Okay, not a problem. Okay, now you see some examples on this. The first one is H2 molecule. You see how hydrogen molecule forms. Hydrogen molecule forms by the orbital overlap of the two hydrogen atom, which has one electron each, and this is the bond formation we have by the orbital overlap. If you draw the orbital diagram here, we have two hydrogen atom. Suppose one is this, and other one is this. Sorry, other one is this. Okay, this is the internuclear axis. Internuclear axis. Both orbital contains one electron, right? One electron, and along the internuclear axis, overlapping takes place, and it forms a sigma bond like this. So this is the axial overlapping we have. We can easily understand this. This line is the internuclear axis. Now the second molecule you see, oxygen, O2. Okay, if you look at the structure of O2, we all know oxygen has a double bond, and each oxygen atom has two lone pair on it. If you try to understand the orbital diagram of O2 molecule, you see the electronic configuration of oxygen atom is 1s2, 2s2, and 2p4. This 2s has 2 electron, and 2p has 4 electron like this. Valence shell is this, right? S has 2 and 2p has 4. So if you draw the orbital diagram of it, I'm going to draw this thing. So 3p orbital, px, py, pz, contains this electron, right? This 3p orbital, if I draw here, I'm not doing anything. I'm just drawing this box in the shape of the orbital. That is it. Similarly, the other oxygen. Now you see, this is the one of the oxygen atom. It contains 1 electron here, right? 1 electron here, and suppose 2 electron. Okay, and like this, we have another oxygen atom also, which has the similar configuration like this. Like this. Okay. Okay, so this has 1 electron, this has again 1 electron, and this has 2 electrons. Now this overlap you see along this line, this is the internuclear axis. And along this line, the overlap that we have, this is axial overlap, which forms a sigma bond. This two orbital goes under lateral overlapping, right? So this is lateral overlapping. So it forms pi bond, right? Like I said, oxygen atom has 2 lone pair. So one lone pair is this, and another lone pair I did not show it here, But this is the another lone pair we have in S subshell. So if you want to show this S subshell electron, S electron here, this is the S orbital, 2 electron present, spherical shape. The another S orbital, you can draw it here for the another atom, and 2 electron we have. So this is the diagram we have, orbital diagram. Did you understand this? Clear? No doubt? Yes. So could you draw the orbital diagram for nitrogen molecule N2? Done? Yeah, hybridization, Mother, just you let it be. We'll discuss it now. Only we'll discuss. Last point, you let it be. We'll discuss. No. First of all, electron won't overlap. Orbital overlap, which contains electron. So when the orbital overlaps, Aditya, so the spin of the electron will change. One is clockwise, other one is anti-clockwise. And that happens on its own in order to minimize the repulsion between the electron. Understood? Hybridization, Shashwat, I won't answer now. Just give me 10-15 minutes. I will explain what is hybridization and then we'll discuss these two. Okay, give me 10-15 minutes. Did you draw the orbital diagram of N2? Correct. So it is very much similar to oxygen molecule. We know nitrogen molecule has nitrogen-nitrogen triple bond and a lone pair on each nitrogen atom. So if you look at the electronic configuration of nitrogen, it is 1s2, 2s2, 2p3. Three orbitals I am drawing here. Okay, each of these orbitals has one electron. Along this line, we have internuclear axis, forms sigma bond. When these two overlaps, all the parallel orbital overlaps. The parallel one, it forms one pi bond. And when these two overlap, it forms another pi bond. And the lone pair is the s electron that we have here in s section. Right? Okay. One more we'll do here. Sorry. The next one we have CH4 molecule, methane. If you look at the configuration of carbon atom, carbon has 6 electrons, 1s2, 2s2, 2p2. Right? So 2s has 2 electrons and 2p has also 2 electrons. Right? This is the ground state configuration. Now you see, carbon is attached with 4 hydrogen atom with a single bond in CH4, right? So for this bond formation, carbon hydrogen 4 bonds, carbon must have 4 unpaired electrons, like 1, 2, 3, 4. Carbon must have 4 unpaired electrons, right? So 2 electrons we have here, unpaired. So what happens to make a bond with the 4 hydrogen atom? This electron jumps into the vacant orbital, and this we call it as the excited state of carbon, which is required for the bonding with hydrogen atom. 1, 2, and 3. This is the excited state here. Right? And all these electrons, orbital, which has one electron, hydrogen overlaps with this 4 orbitals and forms the bond. Okay. So if I draw this structure, we have 3p orbital, and we have one s orbital. Suppose the s orbital is this. Okay. All these orbitals has how many electrons? One electron. Are you getting it, all of you? Please respond. One electron. This diagram, did you understand? Any difficulty in this? It is just the box I have written in the form of the shape of the orbital. Yes, that's right, Madhav. Okay. So what happens after this? The 4 hydrogen atom, which has s orbital, it overlaps with this and forms the bond. All these are s orbital of hydrogen. Right? So it is hydrogen, hydrogen, and hydrogen. All these are axial or lateral. Do we have any lateral overlapping here? Do we have any lateral overlapping? No, we do not have, because we can always draw an internuclear axis like this. Right? So it is, all these are axial overlapping. Okay. So what all orbitals are involved in the bonding? We have one s px orbital, other one is s py. S for which atom? S for which atom here? All these three S for hydrogen, and then SS orbital for hydrogen and carbon, right? So you see what happens here. In the 4 bond, we have different orbitals involved, right? We have different orbitals involved, and when different orbitals are involved, so what we can conclude that the bond forms in CH4 molecule according to the valence bond theory means all the 4 bonds, all 4 bonds should be different, and different in what aspect? Different in terms of their strength, in terms of their length, because different orbitals are there. They cannot be identical basically. Little bit of difference should be there, right? All 4 bonds should be different from each other. Suppose if not these 3 bonds, SPX, SPY and SPZ, at least these 3 bonds and this SS bond must be different from each other, right? Because of the extent of overlapping, right? So this was the conclusion according to valence bond theory. But actually what we observed, but experimentally, but it has been observed experimentally that all the 4 bonds are exactly identical. All the 4 bonds are exactly identical. Hence VBT fails to explain the bonding in CH4. Is it clear? Any doubt in this? To explain the bonding of CH4 and a new type of theory that we get, this theory we call it as hybridization. VBT fails here, and then we got a new theory to explain the bonding here, and that theory is hybridization. Yeah, that's right, Himanshu, correct. Did you understand why do we need this concept of hybridization? Okay, now we'll see. Because the extent of overlapping concept is true for the other molecules like H2, N2, O2. For all these molecules, the theory was perfect, but it does not fit for CH4. Like I said in the beginning, atomic models, we have various theories, right? But all theories does not explain all the property of electrons within an atom. To some extent, one particular theory is correct, right? To some extent, the other particular theory, the other atomic models are correct. So for bonding also, we have different theories, which explains different kinds of molecules, right? So now we'll see what is hybridization, how do we find out hybridization, and how hybridization explains the bonding of CH4 molecule. Okay, so write down the heading, all of you. Hybridization, we know we have already discussed a little bit in the beginning of GOC, right? Write down. It is the mixing of, in short, I'll write down, it is the mixing of atomic orbitals of the central atom with slightly different in energy. Right? It is the redistribution of energy. It is the redistribution of energy and forms a set of new orbitals of equal energy. Means through hybridization, we get a set of new orbitals of equal energy, which is called this new orbital that we have. This we call it as hybrid orbitals. So atomic orbitals, and now this is hybrid orbitals. So how hybrid orbital forms? By the combination of atomic orbitals. So what happens for the central atom? The atomic orbitals of central atom in some molecule combines and forms a new set of orbitals, which we call it as hybrid orbitals. Are you getting my point? Right? Write down all hybrid orbitals have same shape and equal energy. Have same shape and equal energy. So what is the use of hybridization here? What happens in hybridization? We have atomic orbitals of certain different energy, right? But the difference in energy is not that great. Okay, slightly different in energy. Before the bonding with other atom, like in CH4, before the bonding with hydrogen atom, the atomic orbitals of carbons combines and forms a new set of orbitals, which we call it as hybrid orbitals or hybridized orbitals. No, it is not about electron cloud stress. Hybridization is for orbital, not for electron. Electron, you let it be now. Okay. Obviously, electron is present in the atom, but electron cloud is just the density of an electron at a given, in a given area. That is the electron cloud. We are not talking about the position of electron, where the electron is present, right? In which orbital and all. That we are not talking about. We are talking about like we have orbitals, like this. We have orbitals, and this may contain some electron. That's not a problem. This may contain some electron. So before bonding it with another atom, these orbitals combines together. I'm talking about this. And this combines and forms a new set of orbitals. This new set of orbitals, we call it a hybrid orbital. If this has 2 electrons, here also we have 2 electrons, 1 electron, 1 electron, 1 electron. So position of electron is fine. They're exactly same. But I'm talking about the combination of atomic orbital, which gives the hybrid orbitals here. Yes? So yes, understood. Okay, write down the heading. Characteristics of hybrid orbital. First point, write down. All hybrid orbitals have same energy. Already I've given you this. Have same or equal energy. Yeah, it is hypothetical only. Hybridization concept is, it is not hypothetical. Okay. Because we have seen the different shape of orbitals in the molecule, right? That is possible. I'll explain that just a second. I'll take one example and make you understand this, but let me give you the characteristics of hybrid orbital. So all hybrid orbitals have same energy. Like atomic orbitals, hybrid orbital can also accommodate maximum of 2 electrons. More than 2 is not possible. Just a second, Aditya, I'll explain. Wait. Third point. Hybrid orbital always forms sigma bond. Hybrid orbital always forms sigma bond and may contain lone pair. Write down, continue this point. Hybrid orbitals always forms sigma bond and may contain lone pair. Right? So if you remember in GOC, I have told you that while counting the hybridization, we don't count pi bond. Remember that? We just check lone pair and sigma bond. Is it? Right? That is the reason, because it never forms pi bond, hybrid orbital. Okay? It never forms pi bond. It can have lone pair, it can form sigma bond, but pi bond it never forms. So hybrid orbital always forms sigma bond and may contain lone pair. Next point, if there are pi bonds to be formed, then equal number of orbitals then equal number of orbitals must be left unhybridized. Means the number of pi bonds equals to the number of atomic orbitals, okay, which is left unhybridized. So again, the next point is, if there are pi bonds to be formed, equal number of orbitals, atomic orbital you write down, equal number of atomic orbital must be left unhybridized. Done. Again, I am repeating, if there are pi bonds to be formed, equal number of orbitals must be left, atomic orbitals must be left unhybridized. Next point, the geometry of molecule can be determined by knowing hybridization. Okay, geometry of the molecule can be determined by knowing hybridization. So, draw this column here. This side we have hybridization, and this side we have geometry. So if hybridization is SP, then the geometry is linear. If hybridization is SP2, then geometry is trigonal planar. If hybridization is SP3, geometry is tetrahedral. If hybridization is SP3D, it is TBP, trigonal bipyramidal. If it is SP3D2, it is octahedral, or we also call it as square bipyramidal. If it is DSP2, which you won't get here mostly, it is square planar. Yeah, I'll go back. Wait. Copy this down, I'll go back. Done. So this is the geometry you must keep in mind according to the hybridization of the molecule. One last point you write down. The number of hybrid orbital forms equals to the number of atomic orbitals combines. Okay, I'll go back. The number of hybrid orbital forms equals to the atomic orbital combines. Okay. Last point is number of hybrid orbital forms equals to the number of atomic orbital combines. Okay. This table you draw. One side we have the orbital mixed hybrid orbital forms. Okay, so if you are mixing one S and one P, S and P you are mixing, so you will get sp hybridized hybrid orbital. Okay, since you are mixing S and P, if you are mixing one S and two P orbital, then you will get sp2 hybridized hybrid orbital. But how many sp you are getting here? Since one S and one P, two atomic orbital combines, so you will get two sp hybridized hybrid orbital. Are you getting my point? Yes. How many sp2 hybridized orbital we get here in the second one? 2p and 1s. So we'll get 3 sp2 hybridized hybrid orbital. Now in this 2p, we do not know which p is getting getting into hybridization. px-py or py-pz or px-pz, that we do not know. Okay, but we'll have this sp2. When we have s plus 3p, what we get? Quickly. 4 sp3, right? If you have 1d, 1s and 2p, then what we get? 2, 3, 4, 4 dsp2. dsp2 mostly you won't get here in this chapter, but you will get this in class 12 coordination compound, right? We'll see that later. It is 4, not 5. dsp2, it is 4, not 5. If you have 1s, 3p and 1d, that is 5 sp3d orbital we get, 1s, 3p and 2d, 5 sp3 d2, 1s, 3p and 3d, or it is 6, not 5. 1s, 3p and 3d, so you will get 7 sp3 d2. Done, all of you? Last one is d3. What I have written? Acha, d3. Yeah. Copied? Okay. So overall, what happens here in atoms, the atomic orbitals combines with each other and forms hybrid orbitals. Okay, these hybrid orbitals will have same energy, and the number of hybrid orbital forms must be equals to the number of atomic orbital combines. They all have same shape. If you talk about the shape here, Generally, the hybrid orbitals looks like this. I'll tell you here. Suppose one s and one p are combining to form an hybrid orbital. The hybrid orbital that we get is this one. Two hybrid orbital, which is this. This is the orbital we have. sp hybridized orbital and sp hybridized orbital. One s and one p. So generally the shape of hybrid orbital is like this one, right? So we are not concerned with the shape of the hybrid orbital. That is not there in our syllabus. But mostly whenever we draw shape of hybrid orbital like this. One is bigger lobe, other one is smaller one, right? Hybrid orbital. Okay. Now, based on this concept, you see how they explains the bonding in CH4 molecule. Okay. Now you see CH4, like you know, carbon has 6 electron, 1s2, 2s2, 2p2. 2s has 2 electron and 2p has 2 electron. It is the ground state. So in excited state, what happens? This electron jumps over here and it converts into 3, right? It is the excited state. Now, before it makes a bond with hydrogen atom, what happens for carbon? This s and 3p orbitals goes under hybridization, right? So this 4 orbitals goes under hybridization and it forms 4 sp3 hybridized hybrid orbital. Here we have 1 electron. In this hybrid orbital also we have 1 electron like this. You see now the 4 orbitals have equal energy with 1 unpaired electron. And in this hybrid orbital, hydrogen donates its electron, the hydrogen s orbitals overlaps with these hybrid orbital and forms CH4 molecule. So if you draw the orbital representation of it, the 4 hybrid orbital is this. Right? And each of these hybrid orbital contains 1 electron. This is for carbon, right? This is hydrogen, S shape. It overlaps with this orbital with 1 electron. And all these overlap, you see, it is axial overlapping. Right? So all these are hydrogen, hydrogen, hydrogen. The orbitals that overlaps here is all the orbitals you see, it is sp3 s overlap. Here also it is sp3 s overlap. Here also it is sp3 s overlap, and this one is also sp3 s overlap. Correct? So all bond you see contains similar orbitals. That's why the 4 bonds in CH4 molecules are identical and they have the same bond strength and bond length. Did you understand it? So Shashwat, what was your doubt regarding hybridization and VBT? No, it is not there, Shreyas, but yes, like experimentally, once we came to know that all the 4 bonds in carbon in CH4 molecules are identical, then this is the probability, the most probable or most satisfactory explanation of the bonding of CH4 molecule. Like you see, valence bond theory, I told you it fails to explain the geometry, the bonding in CH4 molecule. Then we have hybridization, right? So both are the theories. Both are the theories of bonding, right? We do not have any similarity between the two, right? They explain the bonding of a molecule in completely different manner. Valence bond theory don't discuss about the mixing of orbitals, but hybridization is the mixing of orbitals. Yeah, we'll do a lot more example on this because this is very important. Don't worry with that. But first you tell me, did you understand this? No, it's not. Where is the repulsion? I'm not talking about electronic repulsion here. Vaibhav. Vaibhav, is it? Sorry. I'm not talking about the electronic repulsion. I'm talking about the mixing of orbitals here. Yes. I'm talking about this only. I'm not talking about electronic repulsion. It is just the mixing of orbitals so that all the orbitals will have same energy and they combines with hydrogen atom in a similar manner. No, it's not the only thing. See, the main thing here is, now you see in this CH4 molecule, the orbital that is involved, it has the similar orbital. All the 4 bonds forms by the overlap of sp3s orbital. So similar orbital, we can have similar strength and similar bond length. And hence the bond, all the 4 bonds are identical here. See, one thing here. It's not like they take energy from outside or something like that. When electrons occupy the orbital, it affects the energy of the orbital. The orbital's energy increases a bit. Suppose we have 3 orbitals, px, py, and pz. One of the orbital has electron and other 2 won't have any electron. Then suppose px has electron, so the orbital energy of px is slightly more than the energy of py and pz, right? So in order to have the similar energy, these orbitals intermix and forms a new set of orbitals. So energy is there because of the exchange of electron or because of the presence of electron. No, it has nothing to do with electron pair repulsion, Shreyas. Hybridization is just the mixing of orbitals. Yes, so it is the most acceptable, you can say, or most satisfactory explanation of the bonding in CH4 molecule and many other molecules. Yes, new set of orbitals are purely hypothetical. Yeah. No. Hybrid orbitals always have the same energy. Yeah, before they hybridize, is fine. Before they hybridize, they have some difference in energy. So there only they mix and forms the identical energy orbit. But the difference is not that great. Yeah. Yes. Understood? Shifting of electrons, if I won't say it is not possible. It is possible, and mostly there it is there in case of coordination compound, complex compound. So here you won't get, in simple compound, you won't get shifting of electrons in. See, the thing is, once the hybrid orbital forms, right, then it is, you can consider this similar as atomic orbital. Everything is completely same. The only thing is what? The orbitals, the atomic orbitals which has slightly different energy, they combines and forms the equal energy orbital. That is it. That's why we have redistribution of energy. That depends upon the orbital, right? Which orbitals are there? That depends upon the plane and other thing. Yes, understood. No, we do not have shifting of electron cloud. Electron cloud will discuss when the bond forms, and we'll have the electron cloud between carbon and hydrogen bond. And that electron cloud present in sp3 s overlap. That we can see. Shifting of electron cloud is possible in resonance, when resonance is there. Yes, shares. Yeah. So this is the explanation of CH4 molecule. Like you see, if you try to find out, and hence the hybridization in CH4 is what? And remember one more thing. When I say that find out the hybridization of CH4 molecule, hybridization is only for the central atom. Like we say like this, hybridization of this molecule, but this means what? That we need to find out the hybridization of central atom, right? Because it is the atomic orbitals of central atom which intermix and forms the hybrid orbital. So we always consider the central atom for hybridization, okay, for the calculation of hybridization. Like you see, if I ask you to find out the hybridization of BeCl2 molecule, it does not mean the hybridization is for this molecule, but it means the hybridization of beryllium in this molecule. So in CH4, one last thing, the hybrid orbital is sp3, and hence the hybridization is sp3. BeCl2, you see, beryllium, the electronic configuration is 4 electron, so 1s2 and 2s2. Right? So this is the 2s orbital, and this is 2p. This is the ground state configuration. Since it has to combine with 2 chlorine, so it must have 2 unpaired electron. So in excited state, 1 electron jumps into any one of the p orbital. We do not know which p orbital is it, whether it is psp or pz. Whatever it is, this is the configuration we have. Now, before bonding with chlorine, these 2 orbitals go under hybridization, and it forms 2 sp hybridized hybrid orbital, which has 1 electron each, and these 2 orbitals, the p orbitals, are left unhybridized. Yes. Now this sp hybridized take part in the bonding, and if I draw the orbital diagram, it is 1, 2, 1 electron here, 1 electron here, hybrid orbital. And for chlorine, we have p orbital, that is 1 electron for chlorine. So this is the internuclear axis, you see. And this overlap is sigma overlap. Hybridization for beryllium is sp hybridized. Clear? You see, when it is sp hybridized, the geometry is linear, right? Understood, guys? Any doubt in this? CO2 you try? Hybridization of CO2? What is the hybridization here? Yes, it is a covalent bond. Usually it should be ionic, but for Be and Mg to some extent. MgCl2 it partially covalent, partially ionic. BeCl2 is more covalent, less ionic. Did you draw the orbital diagram of CO2? Achha, you tell me, what is the structure of CO2? Is it O double bond C, double bond O? What is the hybridization of carbon atom in this? Sp. We all know Sp hybridized, right? But you see, we have two pi bonds here, right? I want you to understand the orbital diagram here, because that will, if you understand the orbital diagram, you'll understand the actual concept here. You know, it is sp hybridized, right? Okay, now you see. And we have two pi bonds here, and you also know that hybrid orbital never forms pi bond, right? Now you see. This 2-3 information you have. Carbon has 6 electrons. So 1s2, 2s2, 2p2, 2s and 2p. Okay, this is the ground state configuration. In excited state, 1 electron jumps over here and we get 2s1 and 2p. Okay. Now you see what happens here. Listen to me carefully. Since it has to make a bond with 2 oxygen atom, it means carbon must have 2 unpaired electron present in hybrid orbital. So what happens, this s and one of the p orbitals will take part in hybridization. It forms 2 sp hybridized hybrid orbital, contains 1 electron, this is sp hybridized, and 2 atomic p orbitals will be left unhybridized. And why it left unhybridized? Because I have given you one point in the beginning that if any pi bond to be formed, then equal number of atomic orbitals must be left unhybridized. Yes or no? Tell me. I want you to go through the characteristics of hybrid orbital. There I have given you this point that if any pi bond to be formed, equal number of atomic orbitals must be left unhybridized. Why? Because the hybrid orbital won't form pi bond, right? So since we know this fact that CO2 molecule has two pi bond, so I just left two atomic orbitals which contains one electron each unhybridized, and which we use to which we use to form a pi bond here. Now this orbital diagram I am going to draw here. This one is very it will explain all the concept here. You see, two hybrid orbital we have. Suppose this one is the hybrid orbital here. 1 and 2. Hybrid orbital. Okay. And we have two atomic orbital also. So the atomic orbital is, I am drawing this with a black ink. Dumbbell shaped atomic orbital. We have one more atomic orbital like this. All these orbital contains one electron. So one electron here, one electron here, one electron here, and one electron here. This is carbon, right? The orbitals are sp hybridized. So answer is sp only, that we understood. Fine, it's done. We are trying to understand the bonding here. CO2, right? So oxygen also has, if you look at the electronic configuration for oxygen, it is 1s2, 2s2, 2p4, right? So 2s2 is this, 2p4. In this you see the 2p orbitals has one electron each and one is paired like this. So I'm drawing this p orbital here which contains unpaired electron. This is the p orbital which contains unpaired electron. And one p orbital is this, which contains unpaired electron. The other two, this p orbital has a pair of electron. This has one unpaired electron, this has one unpaired electron. Same thing we have this side also. One unpaired electron for this p. Unpaired electron here and a pair of electron here. Right? So you see along this line, if you can understand this, this is the axial overlapping. Yes or no? Is this diagram clear? Orbital diagram? Axial overlapping. Now between this carbon and this oxygen, two atomic orbitals have unpaired electron. So these two combines and forms the pi bond here. And here also you see the two atomic orbitals which has unpaired electron. This one combines with this and forms a pi electron here. Now you see the pi electron is formed by the atomic orbitals, not by the hybrid orbitals. Tell me, is it clear? Any doubt? No, it is other way, Nishan. The hybridization is sp, that's why it is linear. And how the hybridization is sp? Because we have this explanation. It's not like the molecule is linear, hence it is sp. But it is other way. It is sp, hence it is linear. Yes, 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 we can do that. Wait a second, Nishan. Yes, we have one more lone pair, and that is present in the s orbital. I did not draw it here. This one you can draw it here. See this. This is the s orbital. One unpaired. This is the s orbital that you can draw. What? How do you know that O atoms has unpaired electron in different p orbitals? You can draw the we can draw like this, no? Hence we can fill the electron in the orbital. 2, 4, 5, 6, and then 7. Like 2, 3, 4, 5, and 6. According to Hund's rule, you distribute the electron, you'll get 2 unpaired electron in p orbital. Aditya? Right? Okay. So basically, if you know the structure, and we know the sigma bond and lone pair present on the central atom, right? We can find out the hybridization of the molecule, right? Like this, we can draw the structure and we can find out the hybridization orbital, right? One more example we'll do on this. Try for sulfate ion SO4 2 minus. Try this one. Done. Just give it a try in this. Yes, 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 yes. You have to because there is no other choice, Aditya. You require 4 unpaired electron because SO4 we have. So for 4 unpaired electrons, you have to shift electron from S and P to the D subshell. Okay, fine. You have tried. Now I'll do this. You see, all your doubts will get clear here. See, first of all, oxygen and sulfur will have similar kind of configuration. So for sulfur, if I write down the valence configuration here, valence configuration, it is 3s2, 3p4. So this one is 3s2 and 3p4. And this 3d orbital is vacant, right? Vacant. But since we have 4 oxygen atom, so we must have 4 valence electron here, right? And in order to get 4 valence electron, this will go here in excited state and this will go here in excited state. So what we get here, 3s will have only 1, 3p will have 1 each, and 3d will have 2 electron. Now we need 4 orbitals. So this is 3s, this is 3p, and this is 3d. And sulfate ion, if you know the structure, it is S double bond O, double bond O, O minus, and O minus. All of you know this? Do we have any other option, Vaibhav? In order to get 4 unpaired electron, where those 2 electrons you will shift? Tell me.
Sir?
Yeah.
So, but we don't know where the electrons will go in the 3D subshell, right? It can be
Why?
any of the 5.
We have 3D only. 3p, we have 3D only.
It's
So the
like, but
electron
it can.
goes to the higher energy level. Yeah.
So it can, but it can go in any of the 5, right? We don't know which of the 5.
Yeah, so I'm not saying you it will go into dxy, dyz or where it is.
Oh, okay, okay.
It just go into d subshell. Which orbital we do not know. Because the next higher orbital is 3d, not 4s. The 4s, 3d we have. 4s, 3d we have, but the transition takes place in the same shell, third shell. Madhav. Got it? Clear here? Now, in order to understand this hybridization here, you just have a little bit of information you have. That is, sulfate ion has, yeah, sp3 is fine. Yeah, that's correct. Sulfate ion has 2 pi bond, right? S double bond O, double bond O. It means 2 orbital must be left what? 2 atomic orbital must be left unhybridized, yes or no? Because atomic orbital can form pi bond, hybrid orbital won't form, right? That's why out of this 6 atomic orbitals which contains 1 electron each, 2 will be left unhybridized, that is in the atomic orbital form, right? So what I'm telling you here, out of this 6 atomic orbital, this 4 will go into hybridization and forms sp3 hybridized hybrid orbital, which has 1 electron each. And this 3D electron, 3D orbital will be left unhybridized with 1 electron each, like this. This is 4 sp3 and this is 3D. Is it clear till here, all of you? I'm not drawing here the orbital diagram because this 3D, the d subshell has, the structure of d orbitals is difficult to draw here, so I'm not drawing that. I'm just telling you here that we'll get the structure of sulfate ion is SO42 minus, I'll draw it properly, is S double bond O, O minus and O minus, right? But this orbital which forms the sigma bond, the hybridization of sulfur here is sp3 hybridized, right? sp3 hybridized, and that is the answer. If hybridization is sp3, geometry is tetrahedral. But sometimes they ask this question that this pi bond forms by which orbital overlap. You see, for sulfur we have d orbital and oxygen has p orbital. So what we say, this bond forms by p pi d pi overlap. P pi d pi overlap. P stands for orbital of oxygen that involves in this overlapping is P. The orbital of sulfur that involves in this overlapping is D. And since this overlaps gives you a pi bond, that's why it is P pi d pi overlap. P pi d pi overlap looks like this. This is P subshell and T subshell. Just a second. The P subshell is this and D is this. This overlap we have. See this? If you could imagine, along this line we have internuclear axis and this is the P pi d pi overlap. Did you get it? What you did not understand, Vaibhav? How many of you understood it? Please type in, guys, quickly. No, it is lateral. You see, axial is along that dotted line. This lateral overlap. P pi d pi is this. It's nothing. See, the orbital of s that involves in this pi bond is, you see, it is d orbital involved, right? Atomic orbital is d only, but the orbital of p is oxygen is p orbital. So here we have p d overlap, which forms a pi bond. That's why it is p pi d pi overlap. PD overlap you can write. No, P won't always form pi bond. P can form sigma also. P can form sigma also, mother. The first bond between P and P overlap is sigma only. Yes, understood all of you? Fine. So, to form a sigma bond with S. If SD overlap is there, then it can form a sigma bond. But we do not have SD overlap. So it won't form, no. Okay. Okay. So now whenever you need to find out the hybridization, you have to do all these things to find out hybridization. Okay. Which is time taking. You see, it takes a lot of time to understand the behavior of the molecule and the structure of the given molecule, what kind of bond is present. But always what you can do with the Lewis dot structure, you can draw the structure like this. You can count the number of sigma bond and pi bond, and you can find out the structure here. But we'll do the calculation of hybridization, what is the hybridization of molecule, by a trick, and the trick we are going to use is steric number rule. Right? The concept is that one only that we have done, BeCl2, CO2, and SO4 2 minus. Okay, that is the actual concept. But in the exam, we can do by this rule. It saves a lot of time and effort of you, right? So what is steric number rule? Steric number is number of bond pair plus lone pair on central atom, because we always count hybridization for central atom. Or we can also write this as number of outer atom. Number of outer atom, you know, it is nothing but the number of bond pair. Number of outer atom plus the number of, again, lone pair on central atom. This steric number. Now, based on the steric number, we can write down the hybridization. You see this table here. Steric number and hybridization. With hybridization, you already know what should be the geometry of the molecule. So steric number can be 2, 3, 4, 5, 6, 7. If it is 2, it is sp hybridized. If it is 3, sp2. If it is 4, then sp3. If it is 5, then sp3d. If it is 6, then sp3d2. If it is 7, then sp3d3.
Excuse me, sir, are you talking?
No. Did you copy this?
Yes, sir, we copied.
So, how do you find out a steric number? Could you tell me? I have discussed this already. VSEPR, you remember? How do you find out number of bond pair and lone pair? Right? Valence electron divided by 8. Remember that trick? Yes, correct. No, it's not lone pair plus bond pair. It's Q plus R by 2. Yeah, calculate valence electron divided by 8. Quotient gives you bond pair, and remainder, that is R. R by 2 gives you lone pair. Yes, Q plus R by 2 method. Okay. So Q plus R by 2 gives you the steric number, and then you can find out the hybridization and then geometry and other things, right? So basically that steric number gives you the idea of the geometry of the molecule, of the hybridization of the molecule, plus the shape of the molecule. Geometry, hybridization, and shape you can find out from that steric number. I'll give you some example now, okay? And I want you to do all these. PO4 3 minus I3 minus NO3 minus CO3 2 minus XeO3 F2 IO2 F2 minus and Cl F3. Done? Okay. Okay. So the first one is PO4 3 minus. Okay. What we'll do, we'll find out the valence electron. Tell me the valence electron here. PO4 3 minus. How many valence electron we have? BE is 32. So I'm trusting you, right? I'm not calculating this. So number of bond pair is 4. Number of lone pair is 0. Steric number is 4. Hybridization is sp3. And with sp3 hybridization, geometry and shape both are tetrahedral because the lone pair is 0. I3 minus. The number of valence electron here is 22. So bond pair is 2. Lone pair is 3. Steric number is 5. Geometry is and shape is hybridization we need to write no. So it is sp3d hybridization. Geometry is TBP. What is the shape of the molecule? Shape, tell me. It's linear, right? NO3 minus. Number of VE is 24. Bond pair 3. Lone pair 0. Steric number is 3. Hybridization is sp2. Diagonal planar. Geometry and shape. CO3 2 minus. The valence electron is 26. Bond pair 3. Lone pair is it 24? Let me check. 6 into 3, 18 plus 2, 20, 20 plus 4. It's 24, not 26. It's 24, Nishan. It's 24. 3 and 0. So it is sp2 trigonal planar. XeO3F2. Tell me, valence electron. VE is 8 plus 14. No, it's 40, not 30. It's 40. Yeah. Bond pair is 5, lone pair is 0. So it is sp3d hybridization. Trigonal bipyramidal. IO2F2 minus. Tell me. Valence electron is 14 plus 12, that is 26. 26 plus 7, 33, 34. Because if you want to find out the bond pair and lone pair of electron on the central atom, you need to have the valence electrons. Okay, go back and check where VSEPR, Anurag. Bond pair is 4, lone pair is 1. So it is 5 sp3d. What is the last one? Tell me the hybridization, the last one. Right. Trigonal bipyramidal sp3d, and the shape is T shape. Is it? Yes. So this is for the molecule, inorganic molecule, which is given. You can find out like this, the valence electron. If you have a structure given like this, like suppose we have CH3, C triple bond, C single bond, CH double bond, CH single bond, CH2 single bond, CH double bond, C. find out the hybridization.
So the C to the left of the cyclic compound should be CH, no? Because there are two double
What?
bonds and one single bond.
Yes, tell me.
Sir, I was asking, sir, the carbon which is to the left of the cyclic, the ring, so will be CH, no? So,
This one.
yeah.
Yeah, we have one hydrogen here. That is understood.
No, sir, for the
This
previous
one.
one.
This one.
Yeah.
Right. So I'll do something here. Wait. So I'll add one ring here. Another ring here. And C double bond O and H2. Yeah. No. Tell me the hybridization of each atom, carbon atom. You don't have to name this. Okay, done? Yeah. So the first one I'll write down here only. It is sp3, sp, sp, sp2, sp2, sp3, sp2, sp2, sp3, sp2, sp2, sp3, sp3, sp3. This one is sp3, sp2, sp2, sp2 here. Carbon is sp2, nitrogen is sp3. This is sp3. This is also sp3. This is also sp3. This is sp3. Even this one is also sp3. sp3 and sp3. Right, so if you know the structure, just you count the number of sigma bond and lone pair present on the atom, you will get the hybridization. Once you know the hybridization, you know the geometry of the molecule, you know the shape of the molecule, right, based on the bond pair and lone pair. Okay. all of you? Now you see the another thing here is name we don't do. We cannot, this is not at all required. Okay, it is so lengthy. Okay, so ignore that. Yeah. Fine. So you see, if you look at the structure of the oxygen molecule, we have O double bond O with 2 lone pair on each oxygen atom, and all the electrons are paired. Right? All the electrons are paired. So this particular, distribution of electron according to BBT, valence bond theory, suggests that the molecule is diamagnetic. Right? When there is no unpaired electron, then the molecule is said to be diamagnetic. Whatever the electrons are present, all are paired, diamagnetic molecule. Okay? Weakly repelled by the magnetic field, diamagnetic molecule. If the molecule contains any unpaired electron, then the molecule is said to be paramagnetic. Okay? That is the definition of diamagnetic and paramagnetic molecule. So according to VBT, you see the electrons which are present on oxygen atom, all electrons are paired, and it is said to be diamagnetic molecule. But the actual behavior of oxygen molecule, it behaves as paramagnetic. This observation that is done based on VBT was found to be wrong, because experimentally O2 is found to be paramagnetic. It is weakly attracted towards the magnetic field, right? It is paramagnetic. And hence it is, the bonding or the property of oxygen molecule is not defined by VBT, that is valence bond theory. Okay. And hence we require a new theory to explain the magnetic property of molecule, and that we call it as molecular orbital theory. Molecular orbital theory. So in this also, the orbitals combines and forms molecular orbital, right? But the difference in hybrid and molecular orbital is that in molecular orbitals, orbitals of different atom combines. But in hybrid orbital, orbitals of same atom combines. You look at all the examples that we have done, SO4, CO2, BeCl2, the orbitals that intermix is the orbital of central atom only, one single atom. But in molecular orbital, the orbitals of different atoms combines and forms molecular orbital. That is the basic difference between molecular and hybrid orbital. So we'll see how this molecular orbital forms, right? What are the method we have by the atomic orbitals of the two different atom combines and forms molecular orbital, and how this theory explains the magnetic property of oxygen molecule, right? Okay, so this theory will start after the break. Any doubt in this till here? Any doubt? Fine. So what is MOT? We'll discuss after the break. Take a break now. We'll resume the session at 6:45. Okay, take a break, guys.